Okay, so our first speaker today is Alp Bassa from Boğaziçi University, who will speak on curves over finite fields and their rational points. And I hear that soon he's going to be a full professor there.
Thank you.
Congratulations.
Thank you very much. So thank you very much for the introduction. And before starting, I would like to say that I'm really happy that such an event takes place between mathematicians and number theorists in Turkey and Iran. So for a long time, I think on both sides, people were aware that there are other people working on similar topics. Some maybe had some personal individual contacts, but it's a shame that maybe I shouldn't say it's shame, but it's good that finally there is a more kind of closer institutional bond also among the number theorists. So I was really happy to hear about such an event, and I hope it will continue, and I think it will be very beneficial for both sides. So I would especially like to thank all the people on both sides who initiated such a nice program. So today I'll be talking about curves over finite fields and their rational points. So I'll try to give a kind of an overview of the topic and talk about some recent results of mine. So maybe as a first motivation, let me see, as a first motivation, since this is a number theory meeting, there might be people who are more interested in classical number theory over the rationals and so on. So just as a motivation to say why curves over finite fields might still be very interesting, I always start with such a slide saying that, okay, you have these two parallel worlds. Of course, all of you are aware of this, I'm sure. You have these two parallel worlds of number fields and function fields, and they share many commonalities. So it goes all the way back to the analogy between the ring of integers and the ring of polynomials in one variable over a finite field. So on one hand, you obtain number fields, on the other hand, function fields or algebraic curves over finite fields. And it's in most cases, it's just a translation of language. So on one hand, you will have primes, you'll talk about the splitting of primes and so on, whereas on the other world, you have places and their points. You have the discriminant, which finds an analog in the genus of the curve. You have the class group, which corresponds to kind of the Jacobian. So there are lots of commonalities between the two. So kind of they feed each other, but there are also very big differences, or results in one world can be a good motivation for the other. So one of a good example for this is the Riemann hypothesis, which is a big open question in the case of number fields, but for function fields, it is a theorem by now. So for curves over finite fields, and more generally for algebraic varieties, one knows that the Riemann hypothesis holds for the zeta function that one associates to these curves or varieties. So that's just a motivation why one would still be interested in curves over finite fields, though one does, let's say, classical number theory. Okay, so throughout my talks, he will always denote the smooth projective, absolutely irreducible curve defined over finite field FQ with Q elements. Alternatively, you can think of looking at things more algebraically. You can look at the algebraic function field with full constant field FQ. So I'll stick to the language of curves, but of course, in dimension one, there's a one-to-one translation between those two worlds. So I'll be interested in the set of rational points on this curve. So the set of points that are already defined over the field FQ. And since this curve a priori lives in some finite dimensional projective space, which itself has only finitely many points with all their coordinates in FQ, so must the curve have. So the curve, you know, has only finitely many rational points over the finite field FQ. And then you might ask, what can we say about this finite number of points on the curve? So I'll denote the set of FQ rational points by CFQ. And throughout the talk, I'll be interested in the number of these rational points. This number I'll denote by n or n sub 1. Okay, so let me start with an example. the Hermitian curve. For people working on curves over finite fields, this is maybe the most prototypical example. So whenever you look for extremal cases or counterexamples and so on, the Hermitian curve is a good place to look at. So how is it defined? So I assume Q0 is a prime power and Q is the square of Q0. So Q is a even power of a prime, if you want. And then we look at this Fermat curve defined by this homogeneous equation of degree Q0 plus 1. It is a smooth plane curve of degree Q0 plus 1, so you can calculate its genus. And you can count explicitly how many rational points it has. Namely, it always has Q0 Q plus 1 rational points. This you can see in various ways. One would be to say, okay, if you look at the quadratic extension FQ over FQ0, we have an involution, which is just given by the Frobenius. And then this equation just can be written as, so let me denote this involution by x bar. Then this equation can be given by x bar plus y bar plus z bar. So you want this to be equal to 0. So you have this Hermitian form, and you would be interested in counting isotropic vectors. Or you can use a different model for the very same curve. You can show that you can change the variables and turn the curve into an equation of this form. And then this expression, so this is just a fine model, has the advantage that on the left-hand side, you have the expression for the trace from FQ to FQ0. And on the right-hand side, you have the expression for the norm from FQ to FQ0. And I mean, this is a very standard trick for people working with curves over finite fields, especially working with explicit equations. Over finite fields, we really understand well the norm and the trace. We know how they behave and so on, and you try to use that to say something. So in this case, you're looking for pairs XY satisfying this equation. If you take any value from FQ for the right-hand side for X, the norm will push it down to FQ0, to the lower field FQ0. And then on the left-hand side, you have the trace, and we know the trace is surjective. And for each value that you obtain on the right-hand side from FQ0, you exactly have Q0 squared solutions for Y. And in addition, there is one point at infinity, so you come to the same number Q0, Q plus 1. Yeah? So this was just kind of show what kind of reasoning is being done when working with curves over finite fields and explicit equations. I'll talk more about this in a bit. One thing to notice is that this curve has genus 1/2 Q0, Q0 minus 1. And the number of rational points is Q0, Q plus 1. So you see that the number of rational points is kind of linear in the genus, and the coefficient we have here is just 2 times Q0. And the curve was defined over FQ. So it's basically, we see that the number of rational points is roughly 2 times square root of Q times the genus of the curve. So this will be later on important. So that's why I just stressed it at this point. Okay, so what does one do to say something about the number of rational points? As you all know, sometimes when you want to say something about, let's say, the number of rational points, one single number, it is worthwhile to put everything together into a more complex thing, to put way more information in it than you needed, and to see if you can extract information from this. So that's also done in this case. One defines the zeta function of the curve. So the first versions of the definition go back to Artin. So what you do is you basically don't only count the number of FQ rational points, but you count the number of rational points over all possible extensions of FQ. So for each possible R, I will denote the number of FQ to the R rational points by n sub R. And I put them all together into a nice generating power series like this. So this is the zeta function associated to the curve. So it holds the information about the number of rational points over all possible extensions all possible finite extensions of FQ, right? So a priori, it looks like it holds an infinite amount of information, so to say, because you have this NR for all possible Rs. But it turns out that there is quite some regularity, and you don't really have that infinite amount of information. You can show that the zeta function, which was a priori defined just as a power series, you can see that it converges in a certain domain, and then it converges, in fact, to a rational function. And so this is basically saying that there's only a finite amount of information. You can say way more. You can say that the rational function has a very particular type. Its denominator always has a very simple form, where you only have as information the cardinality of the finite field FQ over which things were defined. And the numerator is what contains all the arithmetic information in this case. It is a polynomial of degree twice the genus. You know, it has coefficients in the integers. So it has a total of 2g plus 1 coefficients. So that's called the Alp polynomial. And as the zeta function itself was just defined by using the count for the number of rational points over various extensions, we hope that we can get some information from here about the number of rational points, and that's indeed the case. So if you look at the Alp polynomial, and if you look at the coefficient of t, namely this a1 here, it is just given by n minus q plus 1. Yeah, so q plus 1 is the number of rational points on the projective line. So a1 tells you by how much the number of rational points deviates from the number of rational points you have on the projective line. And the main ingredient for all of this is just the Riemann-Roch theorem. And as with the classical zeta function, you have a functional equation. It's not too important for this talk. I just wanted to include it in the slides. And most importantly, for this zeta function that you associate to the algebraic curve defined over the finite field FQ, you know that the Riemann hypothesis holds. Yeah, so the zeta function has zeros. In this case, the zeros are just the zeros of the Alp polynomial. You can write the Alp polynomial. You know that the constant term is equal to 1. So rather than looking at the zeros of the Alp polynomial, one tends to look at the reciprocals of the zeros because it's a polynomial with constant term equal to 1. So let me call these reciprocals roots alpha I. They're also called Frobenius eigenvalues. And the Riemann hypothesis for this zeta function associated to the curve defined over the finite field just says that the reciprocal roots all have the complex numbers a priori. They all have absolute value root q. And so this is a theorem by Hasse in the case of elliptic curves, and was later on generalized to arbitrary genus curves by André Weil, and hence it's known as the Hasse-Weil theorem by now. So the Riemann hypothesis is known in this particular case. You might say the classical Riemann hypothesis always has the real part equal to 1/2 line. So where is that? If you just make a small change of variables rather than looking at things in this variable t, if you replace this t by q to the minus s, and this definition in fact makes more sense once you express things in terms of ideals and their norms and so on, as one is classically used to in number theory, then in this new variable s, the roots will have exactly real part equal to 1/2. Yeah? Okay, so the Riemann hypothesis has been proven in this particular case. And then since the zeta function encoded all the count of rational points over all possible extension fields, you expect that from here you get some corollaries for the number of rational points as well. And that's indeed the case. So if you look at how we were recovering this n, the n was just coming from this coefficient a1, and this a1 is just given in terms of the zero reciprocal roots in this form. This is basically just taking this expression over here, multiplying it out, what will be the coefficient of t on both sides? Yeah. You see that the number of rational points is given in terms of the Frobenius eigenvalues by such an expression. And the Riemann hypothesis, or the Hasse-Weil theorem, stated that all of these alpha i's have absolute value root q. So you see that n can be at most q plus 1, plus you can, what can this be? At most it can be is when all of them are as negative as possible, so to say, which means all of them are minus square root of q. You have 2g many of them, so you get 2g square root of q. And this is the Hasse-Weil bound, and it's because it's a direct consequence of the Hasse-Weil theorem, and it is still one of the best bounds we have for the number of rational points. Okay, and similarly, you can generalize this for the number of fq to the r rational points. Here, the q plus 1 will be replaced by q to the r plus 1, and the Frobenius eigenvalues will be replaced by their rth powers. Yeah? But you see that already knowing all the Frobenius eigenvalues, you know all the number of rational points over all possible extension fields. Okay, so just as an example, I just took an arbitrary hyperelliptic curve of genus 4 given by such an affine equation. You can just count the number of solutions of these equations over various extension fields. If you know that count over sufficiently many extension fields, you can see that you can find the zeta function. It has the form that we expect it to have, and you can indeed see that all the inverse roots of this polynomial in the numerator have norm square root of 3 because this curve was defined over f3. And this is just to kind of give a nice example. And when you do that calculation and see that really all roots are nicely distributed on the circle of radius square root q, it kind of gives you some joy. Okay, so now that we have the bounds, the next question you might ask is, how good is this bound? Can it be further improved? And in fact, it turns out that the bound is quite good. Yeah, and as I said, the Hermitian curve gives you always extremal example. It's very special among all curves over finite fields. And the number count and the genus calculation we did before, in fact, if you plug them into the Hasse-Weil bound, you see that you obtain the Hasse-Weil bound with equality. So it is kind of attaining the Hasse-Weil bound. So at least in this particular case, for this particular Q, you can't expect to improve the Hasse-Weil bound without any further restrictions on the curve, because there are curves that attain it. Yeah, such curves are called maximal curves. Okay, but there is still something that you can do. So this was an idea by Ihara. So it took around 50 years after the proof of the Hasse-Weil theorem for these improvements to come. So the idea is in fact very beautiful and very simple. So suppose you have a curve C that is maximal, so it attains the Hasse-Weil bound. Yeah, so if you go back to the expression for the number of rational points, right, in terms of the Frobenius eigenvalues, it's this expression here on top, right? If n is very large, remember these alpha i's were complex numbers of absolute value square root q. So they're all on the circle centered at 0 of radius square root of q. So for this to be large, you need that all of these alpha i's are, so to say, very negative. Yeah? So they should be to the very left of the complex plane, so that they add up to some integer that is very negative, so that the sum will be very positive. Yeah? So to have many points means that all of these Frobenius eigenvalues should be very negative. But then if all of these Frobenius eigenvalues are very negative, so they're to the left of the complex plane, then their squares will be very positive. And the squares were exactly what comes in when you look at the number of rational points over a quadratic extension, right? Remember this expression for an R in general, for R is equal to 2, you see that if you have these alpha I squares appearing, So if you have many FQ rational points, this will require you to have very few FQ squared rational points because of the distribution of the Frobenius eigenvalues. Yeah. Okay, but then you know that all FQ rational points are FQ squared rational. So you have this inequality, plug in everything together, you see that if a curve is to be maximal, then its genus has to be upper bounded by a certain quantity. Yeah? So in fact, it shows that for large genus curves over a fixed finite fields, you cannot hope the Hasse-Weil bound to be attained anymore. Yeah? Because it would violate the fact that the number of FQ square rational points is larger than the number of FQ rational points. Yeah? Another interesting thing to note is that this upper bound that you get for the genus of maximal curves is just the genus of the Hermitian curve. Yeah? So not only is the Hermitian curve a maximal curve, but it is the maximal curve of highest possible genus. Okay, so this led to so the upshot is for large genus curves, the Hasse-Weil bound cannot be improved anymore. So you're interested in what happens for curves of large genus. And for that, Ihara introduced the following quantity. So it's now known as Ihara's constant. So you look at all possible curves C, all absolutely irreducible, smooth, and projective, defined over a fixed finite field FQ. You look at their number of rational points divided by the genus of the corresponding curve, and you look at what the lim sup of this quantity is as you run over all possible such curves defined over a fixed finite field FQ. Yeah? And this quantity is denoted by A of Q. So it tells you what's the ratio of the number of rational points of a curve over a finite field to its genus. What can it be maximally, so to say? Yeah. And if you go back to the Hasse-Weil bound, let me just show you the Hasse-Weil bound again. So that was the Hasse-Weil bound over here. We're fixing the Q, and we assume G is very large, and we're looking at N divided by G. So you see that N divided by G can be at most 2 times square root of Q. Yeah, so the Hasse-Weil bound would give you an upper bound of 2 times square root of Q. Now, Ihara had shown that for large genus curves, this bound is not good anymore. It gives you an improvement of, let's say, a factor of square root of 2, roughly. And then you can do even better. So it was shown by Trinfetch and Vladut that you can have yet another improvement of order square root of Q, and A of Q can be at most square root of Q minus 1. And the idea behind Trinfetch-Vladut bound is basically it's an extension of the idea in the Ihara bound, but rather than comparing the number of rational points over a quadratic extension, you look at all possible degree R extensions and you put that information together in a smart way. Yeah. And as of today, the Trinfetch-Vladut bound is still the best known bound we have for this asymptotic quantity, telling us how many rational points a curve can have for its genus, yeah, for large genus curves. It tells you that you can have at most root Q minus 1 times the genus many curves, yeah, in general. Okay, so that's the best known upper bound. It has not been improved in the last 40 years almost, I guess. But what are lower bounds? How would you obtain lower bounds for such a quantity? One way would be to explicitly construct sequences of such curves with many points. So you fix a finite field FQ, and you want to find sequences of curves defined over FQ, such that their genera tends to infinity, and the ratio of their number of rational points to the genus is as large as possible, because whatever you get as the limit of this ratio will be a lower bound for this quantity A of Q. But then the question is, how do you construct these curves of high genus with many rational points? Because of our understanding of curves of high genus is quite very limited. Yeah? But there have been many ways to construct good sequences. One way was using modular curves of various types, elliptic, Shimura, or Drinfeld type, class field towers, and also by the use of explicit equations. So I will try to say a bit about all of these approaches. Yeah. Okay, so first about modular curves. So this goes back to Ihara and was later on kind of redone by Fassmann, Pladut, and Zink. So this works in the case that the finite field over which your curves are defined is a square. Yeah, so Q should be an even power of a prime. Then Ihara has shown that A of Q is in fact lower bounded by root Q minus 1. Yeah, this was just the upper bound in the Drinfeld-Pladut bound. You obtain the same as a lower bound, so you obtain that A of Q in that part, in this particular case of quadratic finite fields, is given by root Q minus 1. Yeah. And the idea is basically using modular curves. So Ekin talked a bit about these yesterday. So what you do is, so let me show you the proof in the particular case that Q0 is a prime. So Q is just P squared. So you choose a prime L different from the characteristic, which is congruent to 11 modulo 12. And then you look at these modular curves X naught L. So yesterday, Ekin talked about these curves and their models over Q, but you can show that they have a model that has a good reduction modulo P. So you can reduce everything modulo P. You obtain a curve defined over a finite field, over the finite field Fp. You know the genus of the curves. This is basically the Riemann-Roch theorem. It's just given by L plus 1 divided by 12. And then you have many points. So you have the cusps, which will always be rational points in this case. And then you have also, you know, that besides these points on X naught L, other points will be corresponding to pairs of elliptic curves together with some additional structure. In this case, it's the structure of a subgroup, of a cyclic subgroup of order L. Yeah. Okay, so basically the points on these curves will correspond, they form a moduli space for certain objects. So if you want to say there are these points, all you need to do is you need to point at those objects that they kind of classify. And in this particular case, we expect, or the result says that you will get many points over a quadratic extension of Fp. Where do they come from? We know that supersingular elliptic curves together with their subgroups of order L can be defined over a quadratic extension. Yeah, so they will always have a J invariant in Fp squared, and also the cyclic subgroups that form this additional structure that you have will also be defined over Fp squared. Yeah, so since the curve, this curve X naught L, parameterizes, so to say, elliptic curves together with the cyclic subgroups, and you know that these elliptic curves and their subgroups can be defined over Fp squared, you expect that corresponding to these, you will have Fp squared rational points. Yeah, they come from the supersingular points. You can count exactly how many they are using some math formulas. And then if you put this together with the estimates for the genus, or the expression for the genus, you see that the ratio of the number of rational points is just lower bounded by P minus 1 or root Q minus 1. And then if you want the genus to be large, all you need to do is you let this level go to infinity. Yeah, so that's the basic idea behind. And this was the first result, and it gives you the value of A of Q if Q is a square, and it's the only case where we know the exact value of A of Q. Over other finite fields that are not quadratic, there are some results, but we still don't know the exact value. For instance, over cubic finite fields, Zink used the generation of Shimura surfaces to show that you have such a lower bound for A of P cubed. And over prime fields, the only result that we have are class field towers. So I won't go too much into the details about class field towers, but let me just give you the main idea. So rather than looking at the curve, let me look at its corresponding function field. So what you do is you start with a suitable function field and you specify a certain non-empty set of rational places of this function field. And then you inductively construct class field towers. So what you do is you start with this tuple of a function field and a set of rational places, and then you form the maximal abelian unramified L extension of this function field, in which all the rational places that you have chosen, all the rational places in S split. Yeah. So you obtain a new function field, which will in which the places in S will split, and then this will be your new function field, and the places lying above the splitting set S will be your new set of rational places. Yeah? And then you inductively again form the maximal unramified L extension in which the rational places split and so on. So all of these curves will be defined over the same finite field. So this is called the SL class field tower. The L comes from the L extension that we have chosen. And then your hope is that if you can show somehow that this process, this iterative process, does not stop at some point, then you obtain curves with many rational points. And since you have unramified extension, the genus will not grow too fast. So the curves will have many points compared to the genus. Yeah. But how to ensure that this process does not stop? Because there might be no non-trivial unramified abelian L extension in which all of those places split. So for that, one uses very classically some Golod-Shafarevich kind of criteria to ensure that in fact you get the infinite class field tower. And once you have such a class field tower, you obtain immediately a lower bound for the Ihara constant. Yeah. And using this, Serre was able to show that in fact this quantity A of Q is always positive. Yeah, because a priori, it might not be the case that you have families of curves defined over the same finite field FQ, where the number of rational points grows linear in the genus. Yeah? And then it became kind of Olympic discipline in this field to look for good starting points for this iteration. So which function field and which set of places to use to obtain good infinite class field towers so that we get good lower bounds. And so the lower bounds that we had for various primes increased throughout the year in a sequence. And as of today, the best known lower bound we have for A2 is roughly 0.3, for instance, which is still not exactly very close to the Drinfeld-Vladut upper bound, because Drinfeld-Vladut will tell us that it's at most root 2 minus 1, which would be something like 0.4. Yeah? So there's still a gap remaining there. But over prime fields especially, class field towers are the only results that we have. Yeah, because, okay. So yet another approach is by the use of recursive towers. So this has been used by a variety of people. So I also worked on this for a long time. So basically what you want to do is you say, let's not use too much theory. Let's try to explicitly write down defining equations for these curves. And because writing infinitely many equations is difficult, you just say, let me do it iteratively, so to say. Yeah? So you choose a bivariate polynomial, and we call it capital F, yeah? And we recursively define a tower using this F. How does one do that? So one starts first with a plane curve that is defined by this bivariate polynomial we have chosen, right? Of course, in the end, I'll be interested in projective curves and I want them to be smooth. So I will always compactify them and normalize them. But just the affine model, how does it look like a singular model? So you start with a plane curve defined by the spivariate polynomial you started with. The next step, you add yet another coordinate, let's say A3, so that A1 and A2 should satisfy F, and A2 and A3 should satisfy F, yeah, the F you have chosen. And then you go on iteratively like this. C4 is defined as a curve in the four-dimensional affine space where A1, A2, A2, A3, and A3, A4 should satisfy F. So it's kind of a fiber product construction. So you iterate this, and then in the end, you take a smooth projective model corresponding to these singular affine curves that I have defined. And then the question is, how would you find suitable F so that, first of all, you know that all these curves that you obtain are irreducible so that the number of rational points grows fast and the genus does not grow too fast. Yeah? So if you can find suitable such Fs so that you can ensure all of these, then whatever the ratio of the number of rational points to the genus will give you a lower bound for this quantity A of Q, which by Trinfeld-Laudut bound is upper bounded by root Q minus 1. Yeah? And what one does is usually, just as I tried to explain a bit in the beginning for the Hermitian curve, you use kind of norm and trace kind of expressions. Yeah? So for instance, an example by Garcia and Stichtenoth from 96 is you take the F given as this expression over here. Of course, I mean, you have to clear the denominator and so on to get the polynomial. But the nice thing here is that this is the expression for the trace, this is the expression for the norm, and this is again the expression for the trace from FQ to FL, if Q is L squared, right? And then if you want to have many points, you just use the same argument. If you take anything from FQ with non-zero trace, if you substitute it in the right-hand side, you need non-zero trace so that here you get something non-zero. The norm and the trace will push it down to FL. So here you'll have something in FL, and here you have the trace, and the trace from FQ to FL is surjective. For any value in FL that you get here on the right-hand side, you have exactly L many solutions over here. So that's, and then you iteratively will substitute the new thing inside here and go on. Yeah. So that's how you will get many points. The genus computation is a bit more difficult. There's wild ramification involved and so on. So I won't go into the details, but just to give you an idea of what kind of ideas are used. Yeah. Okay, and then over cubic finite fields, various people obtained other expressions giving you recursively defined curves such that the limit of the ratio of the number of rational points to the genus tends to something large. And in each case, they the bound that you obtained is just the sync bounds that was obtained using a completely different method using degenerations of Shimura surfaces, yeah? Which is kind of still at this point looks like an obscure bound, but I'll talk more about this later. So the situation until recently was like over quadratic finite fields, you have the modular curves that give you many their reductions give you curves with many rational points, right? Over prime fields, you have the class field towers, which are kind of not too strong in terms of the bounds, but they at least work. Besides prime field, over prime fields, besides class field towers, there is no result. And then over quadratic and cubic finite fields, there were a certain bunch of recursive equations that worked. And then roughly 10 years ago, together with Peter Behlen, Arnaldo Garcia, and Henning Stichtenoth, we obtained, again, recursively defined towers that work over all non-prime finite fields. Still, they do not work over prime fields. The recursive expression is now given in terms of traces. And in fact, I mean, I don't talk about any of the details in the calculations involved, but to come up with really the right expression that you can iterate and things work well is really a tiring task. Yeah? So if you change the expression a bit, chances are quite high that somewhere in the calculation things will go wrong. Yeah, so these equations that I talked about are in some sense very special. Yeah, and I'll talk about why they are special in a bit. So, so this gives you a lower bound over all non-prime finite fields. It still does not work over prime fields. Over quadratic fields, you obtain the Dirichlet-Vladut upper bound as a lower bound, so you recover the result of Ihara. Over cubic finite fields, you get the same expression as was given by the Zink bound. And over all other finite fields, you obtain a quite strong lower bound, namely, let's say, over L to the n, where n is, let's say, 2k plus 1, because the odd exponents are not that interesting because we know exactly what happens there. So the Dirichlet-Vladut upper bound would tell you you have to take root q minus 1, so L to the k plus 1/2 minus 1 would be the best known upper bound. And what is the lower bound that we obtain? It's a harmonic mean of two quantities, namely one quantity L to the k minus 1, which is a bit smaller than the upper bound, and another quantity L to the k plus 1 minus 1, which is a bit larger than this quantity. But if you take the harmonic mean, you still get something smaller, but more or less at the same order of magnitude. Yeah. Where does this tower come from? I mean, it's given by recursive equation, but in fact, it is very special, and there are other reasons for such a tower to exist. So the idea is you want to find now curves which have many rational points over not quadratic extension, but cubic or degree 5 extensions and so on. So to kind of see where to look for, what we did is we looked at what is done in the proof of Ihara. Basically, using classical modular curves, we obtain, after reduction, curves over finite fields which have many rational points over quadratic extensions. And then the question is, why quadratic extension? Where does this 2 come from? If we understand that, we might generalize it further. And if you go trace back everything, you see that in fact this quadratic just comes from the fact that we are looking at moduli spaces for elliptic curves, which over the complex numbers correspond to rank 2 lattices. Yeah, so this 2 in the rank 2 of elliptic curves over finite fields is the reason why you get quadratic extensions over here. But then, unfortunately, since the dimension of C over R is 2, you have no higher rank lattices. So you can't say, let me look at rank 3 lattices and their moduli space, and then whatever will be the super singular objects will give me rational points in the moduli space defined over cubic extensions. Yeah. Unfortunately, that's not possible. But what you can do is, if you go back to the very first slide that I talked about, there's a strong analogy between the ring of integers and the polynomial ring in one variable over a finite field, right? So how do we define elliptic curves if you want? Starting from Z, we take its field of fractions, we complete at the Archimedean prime, and then we take the algebraic closure. The algebraic closure will be both complete and algebraically closed. And we look at R linearly independent vectors, and we look at their Z linear combinations, right? So we look at Z lattices inside C. Now, here the dimension, while going from R to its algebraic closure, this extension is of degree 2. And hence you have no lattices of higher rank. If you go to the function field world, however, you replace the ring of integers by a polynomial ring in one variable. Right? You take a field of fractions, you complete it at an arbitrary place. Oops, sorry. After completion, you take the algebraic closure. Now, while passing to the algebraic closure, here we had a degree 2 extension. Here we'll have an infinite degree extension. So you will lose that the algebraic closure will be complete. So you have to complete it once more to come to this field C infinity, which will be the function field analog of the complex numbers, right? And then, so here we had another difficulty of having to complete one more because the extension degree was infinite. But now this also is in our benefit because as this extension degree here is infinite, we have arbitrary high rank lattices inside C infinity. So you might then look at FLT lattices inside C infinity of a given rank, let's say rank 3, and ask what is the corresponding moduli space and so on. Yeah? And then you might hope that the super singular objects, whatever they might be, are again, after reduction, defined over, in this case, degree 3 extensions and so on. Yeah? So these lattices are kind of what will correspond to Drinfeld modules. So rank 2 lattices inside the complex plane were just elliptic curves, and the function field analog would be Drinfeld modules. But then you have Drinfeld modules of arbitrarily high rank. Yeah, and a nice thing is that if you look at super singular Drinfeld modules of rank R, then they can be defined over a degree R extension of F cubed, let's say, after reduction. So you get many F cubed to the R rational points on the corresponding moduli space. Of course, now the moduli space, you're looking at higher rank lattices, so you have more degrees of freedom. The moduli space will be higher dimensional. In general, it's R minus 1 dimensional. So you have a R minus 1 dimensional algebraic variety, which has a priori many FQ to the R rational points. And you can point at those FQ to the R rational points by just pointing at super singular Drinfeld modules, so to say. So you just have to find suitable curves that pass through these super singular points. Okay, and if you do this, you obtain, and if you try to find equations for these special curves that we find, so these special curves, they're very closely related to these consecutive minima that were talked about in Ali's talk yesterday. But if you do that, if you find equations for them, you see that they can be given recursively by this expression that you have over here. Yeah, and that's not a kind of a big surprise, because what the idea then is that you have these very special equations, and behind them there's always a high reason why they exist. Also, the very first tower that I talked about using the trace and the norm also corresponds to a tower of Drinfeld modular curves, for instance. So this was noticed, and so all examples that we know of recursive towers that have a good asymptotic behavior, almost all of them have a modular interpretation, which means there is a reason why they are good. Yeah, Elkies called this his fantasia. He didn't call it a conjecture. It's not a well-defined conjecture, but it just says that if you have a recursive tower, which behaves very nice, and such things are difficult to find, you have to be really lucky to find the exact equation giving you such a nice object, then there should be a higher reason why they exist. Yeah? So they should be modular in some sense. And that's still kind of an interesting thing to notice, that when people come up by trying many examples with good equations that define some sequences that have some very extremal behavior, that they define curves with many points, and then it turns out that there is a bigger reason, a higher reason for their existence. Yeah. Okay, so but then still over prime fields, there is nothing. Because what happens is that if you want to work with explicit equations, usually you use like norm and trace kind of expressions. And if you're over prime fields, you don't have them. You can't take the norm or trace to a subfield and work with the norm and trace. And if you want to look at kind of some moduli spaces and kind of get these many points from supersingular objects that they classify and so on. If you look at what could be a corresponding moduli problem, it turns out that the dimension will always be 0. Yeah, so if you look at rank 1 Grunfeld modules up to isomorphism, you have finitely many, so you will not get a curve. You will just get a finite set of points, which will not be useful if you are interested in curves. Yeah. So over prime fields for a long time, there was no result except class field towers. And in fact, many people looked for recursively defined towers. So did I for many years. And after trying many years, I was quite convinced that they did not exist. So that kind of one should sit down and prove that they cannot exist until around 2 years ago, when together with Christoph Ritzenthaler, we found explicit recursively given towers over prime fields. In fact, they work over all finite fields except F2 and F3. You can give them by explicit equations. Yeah, so they're related to some Singer subgroups of the automorphism group of P1. If you look at the corresponding limit they give you, it's quite small. I mean, they don't give you good lower bounds. The lower bound that you get is 2 divided by Q minus 2. So the best known bound by Serre was logarithmic. So it was increasing as Q goes to infinity. At least you got better bounds. This bound even gets worse when the Q increases, and it does not improve the Serre bound for any value of Q. But the interesting result about this is that, I mean, it was believed for many years that these explicit recursive towers over prime fields do not exist. That was kind of what people were looking for, could not find. And what we could obtain was a result that shows that they do exist, though the ones we have found have very bad limits. But our hope is that once there is one example, someone will come and find better examples, giving us better bounds and hopefully maybe even telling us what the exact value of A of Q will be in general. Okay, so I think I will stop here. That's all I wanted to say.
Thank you very much. So we'll look for questions. I guess Ekin has some questions.
Yes, thank you. Thank you for a great talk. I really loved it. I have a very naive question. You said that the method that, I don't know what method you use in the proof, but you said that modular approach would not give you any towers in the case of prime fields, or it was not expected. And the equations are also very, how to say, hard to find or weird to play with. How did you come up with the equations that you have in your theorem?
The very last one?
Yes.
I mean, this one, an interesting thing about this result is, I mean, we have no modular interpretation for this. And we don't know really where this comes from. That's an interesting thing about it. I mean, what happened is I was working on something totally unrelated, and then I can come across these Singer subgroups. And then since for many years I was interested in constructing towers and finding good equations that you can iterate to get nice results, it's kind of whenever I see something that I think, oh, here there is some structure, the reflex is to think, can I use this to construct towers? So I just took this Singer subgroups. So they're just certain cyclic subgroups of order Q plus 1 inside PGL2. And I mean, I did not know of any tower construction based on this cyclic subgroup of order Q+1. I mean, there are constructions using Artin-Schreier extensions or Kummer extensions and so on. Those we understand well, but I was surprised to kind of, it appeared down to me that these particular Singer subgroups have never been considered. So then I just started looking at, can one use them as a kind of a basic building block? As I told you, like these recursive towers you can see as some kind of fiber product construction. So can I use this as the very base of my fiber product? And to my big surprise, it just worked out. And you see, it works already over FQ to the 5, over F5. And over F5, I mean, the extension, the degree of the equation is just 6. So it's not a huge degree that you have. I mean, so it was a big surprise for me that people had not looked at it before. But then I tried to see whether one can understand these better using some kind of, is there some kind of explanation why these curves exist, why these towers exist? Is there a modular interpretation as Elkis wanted to have it? And we could not find any, and that's still something that would interest me very much if anyone has any idea what might be behind these very special curves.
I see. And maybe like once, I mean, if there is such an explanation, do you think there is such an explanation? Do you, like, there's a reason that these equations work? Because my next question would be then, if there is a more philosophical explanation, then there might be a chance to find towers with better bounds, as you said, like with lower bounds. But if there is no explanation, then that would be like end of the end of the road for me.
Yeah, you're very right. I mean, that was kind of my hope. If I find an explanation, I mean, if you just look at the equations, you don't see what you could possibly do to do something better. But if you have an explanation and if you understand what's going on behind the scenes a bit better, my hope was that then you can really improve it. I mean, for now, my feeling is that maybe this is kind of a more sporadic thing that happens. So my feeling is that, in fact, this is an example of a tower which works over not prime fields, but other fields, but you can just twist it into a prime field. That's kind of my feeling, that in fact, it is kind of an object that more naturally lives over FQ squared or so, but then you're just lucky that it is so bad that you can still take a twist and make everything defined over FQ. It's kind of my feeling, but I don't know. I mean, I'm still thinking about it, but
thank you.
Hopefully, maybe at the second meeting of joint meeting, maybe I can say more. Let's see.
Thanks. Thank you very much.
I hope so. Okay, any other questions? Actually, I have one question, but I guess we go with Hadi, then I'll ask one question.
I think this is a very bad question. First of all, thank you very much for your talk. I really enjoyed it. So is it conjecturally expected the EHR constant to be equal to the Drinfeld-Viladut upper bound? To be exactly equal to this?
It depends whom you ask. I mean, so there are many, I know of 3 conjectures about what the exact value would be. So what I believe is that, yes, one should be able to reach the Drinfeld-Viladut upper bound. So that should be the true value for all finite fields, but we just know the most simple recursive constructions, which are bound to give you some rational numbers. If you ask, for instance, Arnaldo Garcia, I mean, he worked on this many years and he really likes this tower that we talked about, and also this lower bound, which kind of recovers both sinc and the Ihara result and so on. So his conjecture is that this is a true lower bound. This is the exact value. I mean, that would be, of course, for us a good thing if we have found the optimal thing, but I'm suspicious about that. And yet another thing is, if you look at this expression and look at what it gives you over prime fields, does not make sense over prime fields. But if you would kind of naively substitute for K1, you would just get 0 here. Yeah. So for K is 1, you just get 0. But we know we have these class field towers that have logarithmic lower bounds. So then Winnie Lee, for instance, suggested that this expression might be kind of a main term that you have. And on top of this, you have some logarithmic things to add. So this would be kind of over prime fields would be 0. So you're only left with the logarithmic things. And for all other finite fields, you have this thing as the main term, plus you have to add some expressions in the logarithm of L. That would be a third conjecture, I guess. But I mean, there's no evidence in either direction. But I kind of believe that we are far from having a good understanding of what's really going on. So I feel that root Q minus 1 should still be possible for all Q.
Okay, thank you very much. Thank you.
Can you hear me?
Yes.
Oh, okay. Because my internet is unstable. Okay. All right. Thank you very much for your talk. Well, actually, this modular interpretation is very interesting. I have a question which probably goes nowhere because of obvious reasons. But the Shimura curves are very notorious for not having global points because, for example, over R, they don't have any points. I was wondering how do they fare over finite fields?
Yeah, in fact, I mean, when I give you this proof over quadratic finite fields, that was just a simplified version. So this using classical elliptic curves. In fact, if you go back to Ihara's initial paper, where he obtained this not over for Q0 is equal to P, but over all quadratic finite fields. But he uses is just Shimura curves in full generality. So they kind of give you, I mean, Shimura curves will really give you, again, over finite fields, an optimal result. And that's exactly what Ihara does. I mean, I just simplified the exposition a bit and just told about classical modular curves.
I see. And how about, I see, okay. So because Shimura curves, let's see.
And I mean, more generally, if you look at Shimura varieties, that's a bit what Zink did when he looked at Shimura surfaces. But he does not give any details, unfortunately. I mean, his result is just like it's a 6-page paper in a proceedings of some computer science conference or so. So it starts with the definition of an abelian variety, and then in the last page, it just gives a very, I mean, it gives the construction, but no results on the calculation. So it would be still interesting to see if one can look at Shimura varieties in general, and maybe using Shimura varieties and certain suitable subvarieties that are just the curves, one could obtain good results over all non-prime finite fields. And maybe one would get the same result as we obtained using Drinfeld modular varieties. I don't know.
I see. That would be interesting because then there would be another parallel between number theory and function theory. No, number theory and function theory. Yeah, I was thinking more in terms of GL2 type varieties and Hilbert modular varieties, parameterizing them.
Mm-hmm.
But okay, that's very interesting. Thank you. Thank you.
You're welcome.
Can I ask another question? Okay.
Sure. Go ahead. Sorry.
So, assuming that the Drinfeld-Vladuth bound is the correct answer, so your conjecture is true. So, what would be the consequences of this? I mean, because I don't have any feeling for this Ihara constant. Are there some consequences of this?
I mean, basically, the Ihara constant is just the very first thing you can ask about high genus curves. I mean, the situation is like, if you are working, let's say, with curves over finite fields, if you work in small genus curves, we have a fair understanding of what's going on. We know more or less, we know their distribution. If someone tells you how does a, let's say, random curve of genus 3 look like, they're kind of good models that tell you how a random curve would look like. But as the genus increases, for instance, if someone asks you, how does a genus 100 curve over a finite field look like, and how many points do you expect it to have, and other specific results about those curves, no one has a feeling of what to expect. Yeah? So we have really no idea how a random or how a generic high genus curves looks like. I mean, there are, of course, some ideas, but nothing too strong. And the Ihara constant is basically just one of the very first invariants that you could have. I mean, you could ask how many rational points can you at most have, so to say, for large genus. So it would tell you something about the number of rational points, what you can at most hope for. So from a number theoretic perspective, I think it's just the first in many questions that you could ask for curves of high genus, but already here we don't have a satisfying answer. So I think that's why many people stop asking further questions. So it's just the first in line of many. But if you think of a more like a practical reason why one would be interested in this, so if you're not only interested from a number theory perspective, there are people who use these curves over finite fields for various combinatorial constructions. I mean, so on these curves, you have basically the Riemann-Roch theorem, which is a very strong theorem. And people use the Riemann-Roch theorem to come up, starting with some nice curves with good combinatorial constructions, you know, of extremal, let's say, expander graphs or codes or other applications in coding theory and cryptography or some other kind of discrete objects. Yeah? So basically what you do is, I mean, if you look at many constructions in, let's say, combinatorial finite field theory, is they go like, take all polynomials of a certain degree and evaluate them at all elements of the finite field and so on. And then you get some very interesting thing, like Reed-Solomon codes or Shamir secret sharing schemes and so on. And then the next thing you could do is you could say, okay, rather than looking at polynomials and evaluating them at elements of the finite fields, let's look, I mean, this would be just looking at the projective line and looking at certain set of functions and evaluating them. Let's look at algebraic curves more generally of high genus and evaluate certain interesting set of functions given by some kind of Riemann-Roch spaces and so on at rational points. And then you really can come up with extremely strong constructions that people using combinatorics are not able to come up with. For instance, in coding theory, there was this question of asymptotic constructions of good long codes and so on, which are known to exist by classical results by Shannon and so on. They are known to exist, but no one could construct them, for instance. And then basically what Gopa did was in the 80s, he showed that you can construct good codes if you have curves of small genus with many rational points. And then Swassman, Vladut, and Zink, using this Ihara result, showed that basically you can beat all bounds that there have been in asymptotic coding theory over the last 50 years. Yeah? So because you know you can construct these curves that are very special, they have some modular interpretation, there's some very natural reason for them to exist, and then you can come up, kind of beat all the other constructions that they are in this field. So if you look from a not number theory perspective, but more for applications, there are very strong reasons to be interested in this A of Q. And I guess why research in the 80s kind of flourished again on curves over finite fields is basically these applications in coding theory and cryptography that came up afterwards.
Okay. So, but thank you very much. So, if the AQ is really equal to the general valued constant, does it have a very strong consequences in either theoretical results or practical results?
Practical is you can construct good discrete objects. Theoretical, it would be more like you can see these. I talked about the Frobenius eigenvalues, which all have absolute value root q, so they're all on a circle. So you can ask how they are distributed. Yeah? So you can ask distribution kind of results for these Frobenius eigenvalues on the circle and so on. And attaining the Frobenius upper bound corresponds to a very particular distribution. So it would say that certain distributions are possible and so on. So it would say something about what are possible distributions of Frobenius eigenvalues, what are possibilities for the number of rational points and so on. I mean, it would still have arithmetic significance, but there would be no big theorem saying like, if this is true, then we can prove this as well. It would be just a better understanding of the situation, kind of.
Thank you very much. Very good. Thank you.
Thank you. Ilan, I guess my internet is unstable, so I rather suggest that Hadi or somebody else.
Okay, so Hadi is now our coordinator, let me say.
Thank you.
Okay, so let's thank Alp again, by the way.